All right, Ozarka again. This is going to be a video on basic rational and power functions and more transformations. So the last video kind of talked about transformations. We're going to talk about them again, so you'll see kind of a review of that stuff, but it's going to be baked into the rational and power functions umbrella as well, so you can kind of understand how these transformations look with different functions. The section objectives are listed right here. The first one is to develop a familiarity with the whole number power functions and basic rational functions. So we're going to go over what a power function is. We're going to go over what a rational function is. So that makes sense. And then once we have that familiarity, then we can apply the transformations to those functions. Intro to polynomials and rational functions. So we were just talking about power functions. You can kind of think of power functions as polynomials, and rationals are basically ratios of polynomials. So if you have a polynomial divided by a polynomial, that's essentially what a rational function is. We're going to go into more detail on rational functions in just a second. But first, let's talk more about polynomials. All right, an nth degree polynomial. So nth degree just means whatever the highest power is, that's considered n. That degree polynomial in the variable x is a function of this form right here, so it's listed right here. It's kind of hard to fully understand what polynomials really are just from that formula. It's kind of best to look at these examples right here to kind of seal the understanding in a little bit more. So this is a quadratic function, this first one, this first bullet point right here. That represents a quadratic function, but a quadratic function is actually a polynomial. And the things that you want to look for with polynomials is the powers are whole number positives, like 2 and 1, or they're 0. So you can kind of see that 1 there at the very end. Well, really this 1 is equal to 1 times x to the 0 power. So it still does have a power, it's just that anything to the 0 power except for 0 is 1. So usually you don't see that x to the 0 there, but really this is just equal to 1. So technically that constant part right here does still have a power with an x. It's just invisible, again, because the power is to the 0 power. I'm going to clean this up a little bit. All right, the next one we're looking at, it's got another whole power right here is 8, and then it's got x to the 0 power. Again, that's invisible, so we don't need to worry about that. All right, the next one, it appears to be a polynomial divided by some other polynomial, because this 2 is actually a polynomial as well. But another way of thinking about it is you can actually distribute that divided by 2 into each of the terms, and you would get 1/2 x cubed minus 1/2 x squared plus 1/2 x minus 1 over 2. So then it ends up still being a polynomial. Everything has a whole number power. You're not really dividing by anything other than that 2, which is completely fine. If we were dividing by 2x or something else like that, it would be a little bit different if we had like a variable in that denominator, and we're going to talk about those in just a second when we go over the rational functions. For now, just understand that if you're divided by a constant like that, it is still technically a polynomial. All right, the next one, 5x minus 7, that's just linear, but it's still x to the first, and then 7x to the 0, and the last one, the 5 by itself, is still 5x to the 0. So as long as those powers, the exponents for each of those terms, as long as each one of them is a positive whole number or 0, then it will be a polynomial. Okay, but if you had something that, like, I don't know, was like x to the negative 1 minus the square root of x or something like that, that is not considered a polynomial, because the x to the negative 1 is a negative whole number and it has to be positive, and then the square root of x is really x to the 1/2, and you can't have a fractional exponent like that. It has to be a whole number. So that's kind of the difference between polynomials and non-polynomials. And we're going to go into more detail again when we get into those rational functions. All right, here's rational functions. A rational function is a ratio of two polynomials. So if you can take a polynomial, divide it by another polynomial, you automatically have a rational function. Because of that, every polynomial is actually considered a rational as well, a rational function. So any polynomial function is a rational function, because technically every single polynomial, it doesn't matter what it is. Let's just say it's, x to the 5th minus x plus 3. This is a polynomial, but it's also rational because you can technically divide it by 1, and 1 is still a polynomial in itself because it's really 1x to the 0. So any polynomial is a rational function. You don't really need to know that necessarily, but it is important just to the distinction of what the definition of a rational function is. The ratio of two polynomials. Now, not every rational function is a polynomial though, because if you're dividing by some other variable, then it would not be considered a polynomial in many cases. For example, this first one right here, this g of x, you can see right away that we can't just like simplify something to get this to be a polynomial. If you wanted to, you can do x to the 3rd divided by x squared plus 1 minus x squared divided by x squared plus 1 plus x over x squared plus 1 minus 1 over x squared plus 1. You're just going to have a bunch of rational expressions here. Each term is technically a rational here, but you can't actually make it a polynomial. All those are going to have powers that are not whole number powers divided by 1, okay, because you're divided by something else. So therefore, it is a rational function, but not a polynomial. Same with this one here, that's rational, but not a polynomial. Now this one here and this one here, these last two, these are still technically polynomials, but they're also rational functions because every polynomial is a rational function. Okay, hopefully that makes sense. If not, definitely ask me in class. We can go over more examples so this makes more sense. All right, reciprocal functions. These are the main rational functions that we're going to be going over in this video. We're not going to do too many crazy rational functions like we just kind of looked at with that one that I just highlighted up here in purple. We're not going to be dealing with that kind of stuff right now, but definitely later we will. For now, we're going to keep it simple. Reciprocal functions. One of the simplest rational functions is a reciprocal function, y equals 1 over x, and I included the graph here. By looking at this graph, you should be able to tell the domain, the range, its end behavior, its horizontal asymptotes, where it's symmetrical, that sort of thing. Not only is it listed below there, but you should be able to tell just by looking at the graph. Okay, the domain, you can notice that the domain is every single x value except for 0. At x equals 0, there is what's called a vertical asymptote. So we have this 1 over x here. Well, if you set the denominator equal to 0, you basically find the vertical asymptote because you can't divide by 0. You cannot put 0 into that y function because then you'd have 1 over 0. And you cannot divide by 0 because it really makes no sense if you think about it. Like you could probably picture in your head dividing something by 2, dividing something by 3, dividing by something by 4. But how can you divide something into like nothing? It doesn't make any sense. It's a paradox in a way. And that's why dividing by 0, no one can do that. It doesn't make any sense to do that. So because of that, x could be any value except for x equals 0. So here's the notation, interval notation for that domain. It's negative infinity to 0. You do not include the 0. Then you union 0 to infinity on there because you don't actually include that 0. Now, the range is the same kind of thing because you can't put 0 in there and you can never actually equal 0. An easy way of testing this out is if you set the numerator equal to 0. So the numerator is right there, 1. 1 cannot be equal to 0. Therefore, you can actually never get 0. Y could never be equal to 0, just like before x could never be equal to 0 because you'd be dividing by 0. This one's never equal to 0 because you can't have one whole thing and keep dividing it up. You'll never get to 0. You get infinitesimally closer to 0, but never actually reaching 0. So because of that, the range is negative infinity. It stops at 0. And then goes from 0 to positive infinity. Okay, reciprocal function is an odd function. An odd function, if you recall, it's when you have a function, f of x, and it's equal to the negative value if you plug in a negative x. Okay, so f of x equals negative f of x. That's considered an odd function. You'll also notice that there's a symmetry along the line x or y equals x. Okay, so here's y equals x. You'll notice the symmetry there. It's another way of figuring out that if it's an odd function versus even. We're going to look at an even function in just a second to kind of review that term as well. All right, the horizontal asymptote, it says as x goes to positive or negative infinity, y is going to 0. Okay, one way of figuring that out, if you have x go to positive infinity or negative infinity, you're basically plugging in infinity or a bigger and bigger number into this x. So you have 1 divided by a bigger and bigger and bigger and bigger number. So it's kind of like the analogy I like to use is if you had one pizza and you're dividing it by infinitely many people. Okay, you can imagine one pizza divided by 2 people. You can imagine one pizza divided by 3 people. But could you imagine one pizza divided by more and more and more and more people? Essentially, you're getting to 0. Okay, and that's actually what's happening here with the horizontal asymptote right there. The horizontal asymptote, it's getting closer and closer to 0. As you can see, the function is getting closer and closer to 0 right there, but it's never actually reaching it because you just keep dividing that pizza over and over again. Now, this is different than the vertical asymptote because the vertical asymptote goes obviously vertical like this. You're getting infinitesimally closer to it. Vertical asymptotes happen when you have a non-zero over 0. So make sure you understand that. Vertical asymptotes is a non-zero divided by 0. And 1 divided by x, you have a non-zero on top because 1 is not 0, and then you're dividing by 0. Therefore, x equals 0 is the vertical asymptote for that. And the horizontal asymptote, so I'm just going to write HA over here. The horizontal asymptote, you have x going to infinity or negative infinity. You're just basically plugging in a humongous number or a super tiny number, just getting more and more negative. So just think of negative a million, negative a billion, negative a trillion, just keep getting bigger and bigger negatively, or positive a billion, positive a trillion, positive, quadrillion, just a bigger and bigger number keeps going. What would you do? What would you get if you plug that into this function here? Well, again, it's 1 divided by infinity is 0. Therefore, that's why the horizontal asymptote is y approaches 0. The vertical asymptote is as x approaches 0, or you can just say x equals 0. And so that's reciprocal functions as well as a review of asymptotes. Make sure you understand vertical and horizontal asymptotes for this class. Next, we're going to go over another simple rational function. It's the reciprocal square function. So it's the same thing as the other one, only instead of 1 over x, it's 1 over x squared. It gets a graph that looks like this. If you notice, there's no negative on there because of the squared. If you have a negative times a negative, it's always going to be positive. So it's a little bit different than the other graph because of that. The domain is the same, though. If you notice, it goes from negative infinity to 0 and then 0 to infinity. You still cannot plug in 0 on this, okay? So the vertical asymptote, non-zero over 0, you can set the denominator equal to 0, which I did right here, and solve this, the square root of both sides, x equals 0. So you have x equals 0 again for the vertical asymptote, which you can see right there. Okay, and then the horizontal asymptote, we have x going to positive or negative infinity, so it's approaching positive or negative infinity. You will notice this arrow here, that is correct math notation. You can't say x equals infinity or x equals negative infinity because infinity is not a value that you can equal, but you can approach it. You can get infinitesimally closer to it, but never actually approach it. Now, if you have 1 divided by basically infinity squared, so this, you're just divided by a bigger and bigger number, what's going to happen here is that the y value is going to approach 0. And if you'll notice right here, we do have a y value approaching 0 on both sides. It's getting infinitesimally closer to it. You also notice it's written down here. It's getting infinitesimally closer to 0, where the vertical asymptote is x equals 0. It's wherever the division by 0 happens. So make sure you understand the difference between those. Vertical asymptotes, non-zero over 0. You cannot divide by 0. Horizontal asymptotes, x is getting bigger and bigger and bigger and bigger and bigger, and that leads to different values. Now, these are kind of a little bit more straightforward. One way of writing, actually, a horizontal asymptote should be written as y equals 0 for this one, and the x equals 0 is the vertical asymptote. One thing we're going to focus on in this video, we're going to do some example problems so you can kind of see what it ends up looking like with those vertical and horizontal asymptotes when it's not just equal to 0. These are just the simple functions, but when we actually do some transformations on them, the values are going to be a little bit different. So let's actually do some of those examples right now. So this first example, sketch the graph of g of x, where it's equal to 1 over x minus 1. Plus 2. So what I'm going to do really quick is I'm actually going to put a graph on there of just 1 over x. And then with that 1 over x, we're going to use our transformation rules to figure out what this g of x function is going to look like. So, all right, so here is our graph of 1 over x. From here, we're actually going to figure out what these transformations are on the g of x function. So it looks like we are going to go to the right 1, and we're going to go up 2. So based on, like, let's just say 0, 0 is our midpoint here, our home base. What I'm going to do from that 0, 0 is I'm going to go to the right 1 and up 2. So you end up with something like this. Okay. Now, because that original 0, 0 shifted that way, we're going to shift everything else that way as well. So let's just take this 1, 1 value right here, this value right here. I'm going to move it 1 to the right and 2 up. So it's going to be right here. And then I'm going to do the same thing with this one right here. I'm going to go 1 to the right and then 2 up. So it's going to end up right here. Now I'm going to erase that other middle point right there because we don't really need that anymore. That was just kind of used to figure out what this graph's going to look like. And then we can just kind of sketch here like this and here like this. Okay. So you can see it was basically the original graph, but it shifted to the right 1 and then up 2. Now it doesn't need to be exact. It does say sketch it, so that's kind of why it looks like that. But we can use this to figure out what our domain and range is. So the domain right here, it's actually going to be the same. Just because everything shifted over, it's not going to change much, except the one thing that's going to change because it moved to the right 1, instead of not including x equals 0, now it's not going to include x equals 1 because you can kind of see there's a vertical asymptote at x equals 1 there. So what we're going to do is we're going to write negative infinity to 1, union 1 to positive infinity. Those are the only x values that you can have for the domain. The range also changed because the first time you couldn't have y equals 0, but since this moved up 2, now you'll notice that the horizontal asymptote is right here at y equals 2. So you can have every single y value except for 2. So it's going to end up being negative infinity to 2, union 2 to infinity for the range. Now the asymptotic behavior, what are the asymptotes for this? It's just going to be x equals 1, as we kind of just talked about just a second ago. Vertical asymptote there, and the horizontal asymptote is going to be at y equals 2. So that's basically the answers for all of these. All right, onward to the next one. The next one says determine the horizontal and vertical asymptotes for this graph. Okay, so now I have to actually use the information of how to find vertical asymptotes and horizontal asymptotes with a different problem, not just that standard reciprocal function. Now you can see it's just a reciprocal square function that has some transformations on it. The main thing you have to do for vertical asymptotes, it's non-zero over 0. So what you need to do is basically set the denominator equal to 0. You can see the numerator is non-zero, so you know it's a vertical asymptote right away because of the 1. And you're basically just setting that x plus 7 squared equal to 0. Or you can just think, what do you plug in to make that 0? Obviously, it's going to be -7. But if you wanted to, you can just do the full math on this. Take the square root of both sides, -7 on both sides, and then you have x equals -7. So that's the vertical asymptote. Horizontal asymptote, now we have x going to infinity and negative infinity. So basically, that x in the x plus 7 just becomes bigger and bigger and bigger and bigger. So you end up having 1 divided by an increasingly bigger number. This whole thing just basically goes to 0. So you have 0 minus 8, so this one's just going to be y equals -8. And again, the reason for that is with horizontal asymptotes, your x value just gets going to infinity. If it's going to infinity, you have 1 divided by infinity plus 7 squared. That's just a huge number. 1 divided by a huge number is essentially going to 0. 0 minus 8 is -8. So that's basically how you find vertical and horizontal asymptote. All right, this next one says sketch a graph of f of x and it's equal to -2 over x squared. So in order to do this, what I'm going to do is actually get the parent function, the original function of that 1 over x squared again, and then we're just going to do a transformation based on that since it's just times -2. All right, so here's a graph of 1 over x squared, and we're going to apply the transformation that's given on this, namely that this is just going to be -2 times 1 over x squared. So basically all the y values are just multiplied by -2 essentially from that original function. So because of that, they're going to be flipped on the sign. So instead of being positive, they're going to be negative, and instead of being multiplied by 1, they're going to be multiplied by 2. So they're going to be double the value, but also negative. So to do that, first thing I'm going to do is find these nice points that are on here. So 1, comma 1, -1, comma 1, and I'm just going to multiply both of those by -2. So this one right here is going to be -2. So now it's going to go down here. This one's going to go down there as well. Everything else basically just flips, but it's nice to pick numbers that are kind of just easier to look at with that. So after I have these points, I want to make this a little bit steeper than what it is currently. So it kind of I don't know, grows a little bit faster in a way like this. Obviously, this is not a very good sketch, nor does it really need to be, just to get the idea of what's going on here. So it should be growing twice as fast, and it's obviously pointing in the opposite direction because of that reflection. So that's that problem. Next, we're going to go over even-numbered powered functions and odd-numbered powered functions. And to do this, I'm actually just going to use Desmos because I feel like it illustrates this whole point very well, and you get an idea of what's going on with this. All right, so right here, we have a graph of f of x, and basically I put certain values in here. I have the a value, I have this b value, which is being subtracted from the x directly right here in the parentheses. It's squared, so it's an even power. We were just talking about even powers versus odd powers. This is going to hopefully showcase this a little bit more. And then we have the plus c right here. And this is all designed to basically just set this whole thing up in Desmos just to kind of show you the transformations in real time. I can mess with these values, the a, b, and c that are underneath this function, and it's going to give the graph some character. Okay, first thing I'm going to do is I'm going to make a 1. So I'm just going to move this over right here and make it 1. So that means if this is 1, it's just x minus b. b is 0, so it's just x squared plus 0 because c is 0 down here. Okay, and if you notice, if I change 1, it gets steeper and steeper. It's just kind of like that last video talked about. If you multiply by a bigger and bigger number, the y value gets bigger, which means it gets steeper and steeper. It grows a little bit more. So it's almost like it's being compressed horizontally. Okay, if I go back to 1 here, you'll notice it's opening upward. By the way, anything that's an even power like this, I'm gonna actually write this in here. Anything that's an even value like this, so even powered functions have the ends going in the same direction. So if you notice, both of the ends on this are going upward. So even powered functions have the ends going in the same directions. This even happens if I change a to -1. If you notice, they're still pointing in the same direction. They're just going downward because of that negative basically reflects along the x-axis. And if you notice, if I make it more and more negative, it just compresses it more and more. It climbs a lot faster versus the opposite. And what's kind of cool about Desmos too is you can just kind of hit play and you can kind of see the trend happening in real time. It's widening out, zeroes out, compresses, widens out. You get the idea. All right, I'm just going to keep this at 1 just so it's kind of nice. Okay, this b right here, it's x minus b. And if I increase this, so if I make b a positive number, we're subtracting by a positive number, you'll notice it actually moves to the right. Okay, this is what was discussed in the previous video as well. Okay, if I go the opposite direction, it's going to go left. If I start turning negative, now it's a minus minus, so it's plus, it's going to go to the left. It's almost like the opposite of what you think would happen. And if you hit play, you can kind of just see it, I don't know, dancing around like that, back and forth, just to kind of get the idea of that trend. Just to give this more character, I'm going to, I don't know, put b is equal to 2. Yeah, we'll keep a as 1. And then c, if you recall, if you change this, it's just going to go up and down. So it's positive, it's going up, negative, it's going down. This is kind of a little bit more common sense. where it's like kind of what you see is what you get if you go up or down based on positive or negative. Now the b is opposite. That's why I put it's x minus b. So while we're going positive here, it is still minus over there. So it's kind of opposite of what you think it would be. Let's keep that at 3. We'll keep the c at -2 just to kind of get an idea of what's going on. And if you notice, the vertex here now is 3, -2. The point where that turning happens, which matches what's our b and our c. So our b is 3, our c is -2, our vertex is 3, -2. And it is important to note that this is going to happen no matter what the power is, as long as it's even. So say I change this to a 4, you'll notice it still has the same shape, it still has the same vertex, it's still a U, it's still pointing in the same direction, but it kind of flatlines a little bit more. It flattens out, gets a little steeper kind of in the middle. And change it to a 2 and then compare that to a 4. Okay, now compare it to a 6. Compare it to an 8. Okay, in fact, I can compare it to a 10, but I can even make this like 100. And if you notice, it gets really, really boxy. Okay, it almost looks like it's like a right angle almost, but it's not. If I zoomed in, you would actually see that it is curvy. Zoom back out there so you kind of get the idea. But anytime that it's an even power, you'll notice that it goes in the same direction. Okay. Now the opposite is true if we change this 2 to an odd powered. So if I change this to a 1, you'll notice it goes in opposite directions. Okay, so what I'm going to do is copy and paste this and make another note here, and I'm going to say odd powered functions have ends going in opposite directions. Okay, and it doesn't matter what a is, so I'm just going to hit play for fun here, and you'll notice it goes really steep, and then it goes the other way, still goes negative when a is negative, and flips the other way. Okay, we'll keep this, I don't know, let's just keep this at 2. B does the same thing, it's either moving it left or right, so that doesn't change at all. And then the C right here, if I change this, it still goes up and down. It's kind of hard to see that go up and down, it almost looks like it's moving diagonally. So let's actually give this a little bit more character. Instead of a 1, let's give this a 3 for a value. Now we see this little bend right here. Let's see here, let's move this down a little bit. You can kind of see that bend there, so it kind of gives us a little reference point in a way. Same thing happens with the A. You'll notice it's going to compress and widen out, but you'll also notice the odd powered functions ends go in opposite directions. It doesn't matter if A is positive or negative, it always just flips and goes back to a negative direction. Okay, and if I change B right here, you can kind of see it's easier to see that it's moving left and right. Same with the C here, if I change that, going up and down, it changes value. So that's a video on basic rational and power functions, as well as the review of what these transformations do to these functions. If you notice, it doesn't matter what the function is, as long as you do that transformation with the correct rule, it's always going to apply. The graph is just going to kind of change shape. So make sure you get the shapes of all those graphs memorized. Make sure you understand what they look like. It's kind of like zookeeping with functions, but make sure you understand what they look like. You should be able to look at them and figure out, is that a square root? Is that a polynomial? Is that a quadratic? Is that a absolute value? You should be able to look at those and figure out what kind of function it is based on its parent function. So if you have any questions about anything in this video, let me know.